Okay, so everyone must, well, for each style, then there must be one swimmer which covers that piece of the medley. Okay, so this is the optimization problem that we just set up. So here I'm using the indices R and C. R is for rows and C is for the columns. Okay, and it's the same as on the whiteboard. What kind of optimization problem is this one? Remember, we had MI NLP, MI-QP, MI-LP, I-NLP, I-QP, I-LP, B-NLP, B-QP, B-LP. Essentially, the more you go to the end of what I just said, the easier the problem becomes. So that's why it is important to know what kind of problem are we going to solve. So, do we have continuous decision variables? No. So we are not in the mixed case. We are only in the integer or in the binary case. Now we say, okay, so from those integer variables, are those really integers or just binaries? Well, they are just binaries. Okay, so we are in the B case. And among the B case, we still have three options: binary nonlinear program, binary quadratic program, or binary linear program. What conditions have to be satisfied for something to be a linear program? What must be the constraints and what must be the objective function? The objective function must be linear, but what about the constraints? They must be linear as well. Are they? Are these constraints just linear functions of the decision variables? Well, sum is a linear operator. Okay, just summing up. That's a linear function. So this constraint here is linear for each column. These constraints are linear for each row. So we are in fact solving a binary linear program. Okay? And yet again, this kind of optimal composition that occurs very frequently. By the way, what we are essentially looking for here is the so-called permutation matrix, which tells us like who will be the first one for the freestyle, who will then swim the breaststroke. Actually, I messed up something here with those circles. They have moved, so that one should be here clearly. That's a mistake on my side. I apologize. Okay. So what we are looking for is a permutation matrix, and the permutation matrix has this strong property that it has exactly one element in each row and exactly one non-zero element in each column. Okay? And these kind of binary permutation matrices can be also used to solve a problem which I'm confident you have already heard before. It's one of the most famous optimization problems in the world. It's called the traveling salesman problem. So essentially, we have a set of cities. There are roads connecting these cities. Those roads have different lengths. And we would like to devise the path of minimal distance which passes through each city exactly once. Okay? And actually, this is one of the most general difficult optimization problems in the world. And maybe you have heard about the question to which nobody knows the answer to. And the question is whether P is equal to NP. Anybody has seen this? P is the set of problems that can be solved. Well, first I give the technical explanation and then the natural one. This is the set of problems that can be solved in polynomial time on a so-called deterministic machine. This is the set of problems that can be solved in polynomial time on a non-deterministic machine. Non-deterministic means a random machine. If you have a random machine, you have some non-zero probability of just doing this and having the optimal solution. Because you are just picking one solution like on a probability basis, and there is always non-zero probability of choosing exactly the optimal solution. Okay? In simple terms, this is the set of problems that are easy to solve. This is the set of problems that are very difficult to solve. linear and quadratic programming are in this category. They are relatively easy to solve. We know that to solve a quadratic program, essentially all we need to do is to do a bunch of matrix inversions. We know that a matrix inversion takes time roughly n cubed, where n is the number of decision variables. So even if we have to solve a bunch of them, it just means we are solving k times n cubed kind of problems. Okay? Each of these problems here, it takes some time, and we are multiplying it by the number of problems that we need to solve. The bottom line here is that the overall time to solve a quadratic program scales cubically with the number of optimization variables. This is a polynomial dependence on the number of optimization variables. The complexity of these problems sometimes, well, very often is 2 to the power of n. This is not a polynomial dependence. Essentially, a polynomial dependence means that as your problem grows, also the time grows, but not as much as it would with these kind of algorithms. Essentially, 2 to the power of n scales like this. Okay? So essentially, we are only able to solve small problems, while with these algorithms here, we are able to solve large problems. Or conversely, if I have a problem of the same size, say this would be the n here, then the p-class algorithms would be much faster compared to the NP class algorithms. So these are NP algorithms. So we have a set of easy problems, and we have a set of problems that are very difficult to solve. And the question which is unsolved up to this date is whether for each difficult problem there exists a simple algorithm. And this question very frequently occurs in this concept here, because we know that the complexity of that problem is actually even worse than that. It's n factorial. Because we know that there is a naive way how to find the traveling salesman optimal path. Just try out all possible combinations. The only problem is that there are n factorial combinations. And n factorial grows even faster than 2 to the power of n. Okay? So if somebody would provide an algorithm which solves the traveling salesman problem fast enough, he would be either very rich or very quickly dead. Very quickly dead because if you can solve traveling salesman problem effectively, it means you can also factor prime numbers very effectively, which means you can crack all those advanced encryption algorithms very easily. And we know that all those SSL certificates in the web world which protect, for instance, banking transactions. Essentially, if we can provide an effective algorithm for the traveling salesman problem, you can easily crack any encryption in the world, which means there are many people who would love you not to share that kind of algorithm. Okay? Fortunately, you don't have to fear anything because many people have looked at this and they couldn't come with an effective algorithm for this problem. To solve it optimally, what they were able to do is to provide approximation algorithms which are very fast, but can only provide a path which is, say, 2 times longer than the optimal path, which is still a good result, because if you take any path, it will be like 10 times longer than the optimal path. So if you have an algorithm which at least gives us that 2 times worse than the optimal solution, that's already a pretty good result. But it is not sufficient to crack those encryption algorithms. Okay? So this traveling salesman problem is used as a good example of those NP hard problems. Problems that are very difficult to solve as the number of optimization variables increases. So the number of optimization variables is proportional to the number of cities that we need to visit. Okay? If we would be able to find a good algorithm, well, that would show that P is equal to NP, and you would be very, very famous. Okay. So the traveling salesman problem is a binary optimization problem which can be solved using, for instance, the permutation matrix. But there are other effective ways, well, semi-effective ways how to solve these kind of problems. Okay? So that would be our third example of where binary and integer optimization is used. And let us now take a look at the final example, which I will use till the end of the lecture, which is kind of interesting. Again, it's a very general type of problems, and I'm going to present one possible interpretation, but there are certainly more. So we are going to look at the warehouse location problem. Sometimes it's also called facility location problem, because we are not, strictly speaking, restricted to selecting warehouses, but we can select like production facilities and anything else. So the problem starts like this. We have a set of customers that we have to serve. Each customer requires DI amount of products that we ship to him. Okay, so that's the demand that we have to satisfy. And we can satisfy this demand by opening a warehouse which contains the products, which are then shipped to individual customers. The shipping here, the shipping cost, is basically proportional to the distance of the warehouse from the customer here. And we assume that we have just some per unit shipping cost. So this is the shipping cost from the first warehouse to the first customer. So the first index will be for the warehouse, the second one for the customer. The warehouse here has some storage capacity, so it has only that amount of products that we can ship. But it actually also has some fixed cost, meaning if we decide to build that warehouse, annually we have to pay this amount of money. Okay? If we decide that it is worthwhile, we might open a new warehouse, because that one would have probably different distances here. It might have different fixed cost and different storage here. And we don't have to stop here. We can open pretty much as many warehouses as we want. The question is, which warehouse to open, such that we minimize the overall cost and we satisfy the demand? That's the problem that we are going to look at here. Okay? So we would actually have continuous optimization variables, which are the amounts of products that we ship through each of these routes here. These are continuous variables. So it means that we can also ship a kind of fractional number of the products. And then we have binary variables, which are 0, 1, and they mean whether we open the warehouse or not. Okay? So we have continuous variables and we have binary variables. And by the way, yeah?
There is one question. Do we have to satisfy the whole demand, or do we have just to maximize the?
We have to satisfy the demand of each customer, and we have to satisfy it exactly. So, but it also means that if this guy requires 5.5 units of something, we can give 3 units from first warehouse and 2.5 from the second warehouse. That we can do. These kind of problems also occur frequently, for instance, in network traffic routing. Okay, so you are essentially trying to come up with the location of your data centers, such that you satisfy some demand from your customers, and you certainly have some fixed cost. You have to build that data center. You might have constraints on these shipping routes here. I'm not going to consider them here, but they are very easy to add. Like through each channel, we can only ship this and that many products. So this is the problem that we are going to look at, and we will actually use it as a motivating example for some really funny stuff that will come in a second. But before that, let's take a look at how this problem is even formulated. Okay? And this will take some time and your assistance, so let's try to do that. So again, step number 1. Let's introduce the constants and variables that we will use in our optimization problem. Okay. So we already see that we have C. Okay, and let me first say that the index I will be for the warehouses, And we might have warehouses from 1 to m. Okay? The index j will be for the customer. And we have m of those customers here. Okay? So then we have Cij as the shipping cost of 1 unit of the products from the i's warehouse to the j's customer. Okay? So that's the cost. That's just a constant. The actual amount of products that we ship, we will call Xij. So that's the actual number of products shipped from the i's warehouse to the j's customer. And we will have binary variables yi, which denote whether we open the i's warehouse or not. So yi is equal to 1 if the i's warehouse is open, and it is 0 otherwise. So these are the optimization variables, and we have a couple of more constants here. So we have dj as the demand of the j's customer. We have fi as the fixed cost of the i's warehouse. And we have si as the storage capacity of the i's warehouse. And these two guys here are optimization variables, and the rest are just constants. Okay? So using this nomenclature here, let us try to formulate the optimization problem. So the objective here is to minimize the overall cost. The cost consists of two types. The first one is the operational cost, which means the cost of transportation from warehouses to customers. And then the second part is the fixed part, which is associated to the fixed cost of running a particular warehouse. And we would like to minimize the overall cost. So what would be the operational cost? What is the cost of transportation? The overall cost of transportation. What is the cost of transportation from the i's warehouse to the j's customer? Cij times the transported amount. Okay. That's for one customer, one warehouse. We are interested in the overall transportation cost, so we have to actually sum it up through all customers and sum it up also through all warehouses. Okay? So that's the operational cost. Now, what is the fixed cost of operating the warehouse? That's the fixed cost times yi. That's the cost of operating the i's warehouse. Okay? If the i's warehouse is decided not to be open, then this is just 0. Okay? And we have to sum it up over all warehouses. Okay? So that's the cost function. Now, what about the constraints? So the first constraint is we must satisfy demand for each customer. So for each customer, for all j, what must hold? that the amount of products shipped in to the customer is equal to dj. Right? How many products do we ship from all warehouses to the j's customer? Xij means from the i's warehouse to the j's customer. Now we keep the j fixed, and we want to know how many products arrive to the customer. So we have to sum up this quantity for each warehouse. Right? So the sum of Xij over the warehouses must be equal to the demand. And this constraint we actually have to repeat for each customer, because each customer has a different demand. So that's constraint number 1. Constraint number 2 is that we are only allowed to ship the products towards the customer. We are not allowing, like, sometimes it might be beneficial to say, we export here 10 items, 5 will be kept here and 5 will arrive at the other warehouse. We are not allowing this situation. Essentially, we have to respect these arrows which say the products flow in one direction. How can we do that? What would be the constraints? Xij is the amount of product. If there would be a product going in the opposite direction, it would mean a negative flow. Okay, so we essentially want to say each flow must be non-negative. So this is for each warehouse, for each customer. So that's our next constraint. Then we have this binarity of those y decision variables, which mean whether to open or not to open a particular warehouse. So we add them. Yi is a binary variable for each warehouse. And now comes the interesting part. We must tell the optimization problem that if it decides not to open this warehouse here, then it also cannot take anything using these transportation channels. And we also need one more constraint which says that the number of products that we take from the warehouse does not exceed the capacity. So let's try to do that constraint first, because we will see that the constraint before comes naturally. How do we say that the amount of products extracted from the warehouse does not exceed the capacity of the warehouse? So for each warehouse, what must hold? So the sum of items transported out of the warehouse, so the sum of Xij over all customers, does not exceed the capacity of the warehouse, right? What is the capacity of the warehouse when the warehouse is not open? 0. What is the capacity of the warehouse when it is open? 1 times Si. So how can we modify this constraint to actually account for the fact that... So essentially what we are saying is, this right-hand side should be either Si if the warehouse is open, or it must be 0 if the warehouse is closed. Does this make sense? It does, right? Okay, so how can we now include this if-then statement here? How can we equivalently write this one? Right? This is like constant times Si here. Okay? So essentially this is 1 times Si and this is 0 times Si. Okay? And this constant here accidentally is the same value as Yi has. Right? So it's essentially we can like merge those two constraints together into this form here. And it will tell the optimization that if it decides not to open the warehouse, then it will also not be able to take anything from the warehouse. So if the demand requires us, or if the cost function allows us to open a warehouse, we will also open up its capacity towards the export from the warehouse. Okay? And this is exactly how the problem is formulated at the end. Okay? So what we have here is a mixed binary linear program. Well, these programs, they are just called mixed integer linear programs, even though these decision variables are just binary. Okay? So we have continuous decision variables, which are the x's. We have binary decision variables, which are whether to open the warehouse or not. And we have a bunch of linear constraints. So here, notice that x is a decision variable, y is a decision variable. We have no product between these two, so this constraint is just a linear constraint in x and y. Okay? And this is a cost function which is also linear, so this is really a mixed integer linear program. And you will practice with these kind of problems, and they are quite fun. Okay? By the way, it might be also possible to change this problem to account for the fact that we can only ship integer amounts of products. That's very easy to do in a mathematical side. Essentially, what we will do is we will say xij must be inside of some finite integer set. What is a small change for the whiteboard is actually a very big change for the algorithm. Solving this problem is rather easy even if you have a large number of warehouses, say 10, 20 or something like that. Once you start assuming an integer amount of products, you will probably only be able to solve the problem for 2 warehouses. The complexity which comes from the integer component would be so huge that it would essentially prohibit us to solve this problem for some large class of problems. Okay? So this is the warehouse location problem, which occurs in practice in multiple forms. Okay? These might not be warehouses, they might be factories, and these might be the warehouses as your customers. You might introduce a completely new layer, like you might have warehouses, but on top of that you might also have factories which provide the warehouses with the products. So you essentially, by this problem, we can model the whole distribution network. And these kind of problems, they are very important in practice, and that's why it is important to know how to formulate these problems. And then you will see in the exercises how to translate this mathematical description into YAML and from there how to solve these problems. Okay? So this is the warehouse location problem, or a more general facility location problem. So let's have now some fun with this problem. What if the manager of the whole company decides that at most k warehouses can be open? We are going to optimize where they should be, but at most k can be open. How can we add this condition into our optimization problem? How many warehouses are open? How do we know that? How do we know how many are open? Which variable tells us a warehouse is open? Yi. Which variable or which combination of these variables tells us how many warehouses are open? It's just the sum of yi. Right? That's the number of warehouses that are open. So if we want them to be smaller than k, we just add this constraint to the optimization problem and the requirements are respected. Okay? So what we are going to do now is we are going to introduce additional constraints which model some real-life situations. Okay? And this might be one of them. We can twist that. At least k warehouses must be open. What do? We just swap that inequality. Sometimes we want to say exactly k warehouses must be open. In that case, you would add an inequality constraint, right? What if we don't want exactly k warehouses to be open, but say we might optimize over 10 warehouses? And the manager says, exactly one of the first, third, and fifths must be open. You know what that means? 2, 4, 5, 6, we don't care. How can we write this condition into our optimization problem? Look, I mean, it's pretty much the same as here, just that we say not exactly k, but exactly 1. And we are not going to take the whole sum, but only the sum over the first, third, and the fifth element. Okay? So that's the condition. y1 plus y3 plus y5 is equal to 1. So it really fits into the same framework. Okay? And we are just starting. There is nothing. These kids play. Okay? So let's make it interesting. At least one of warehouses number 1, 4, and 5 must be open. It is no longer so easy. And we will see how to formulate these kind of problems in a second. But we will not stop there. We will also be able to write something like that. Warehouses 1, 4, and 5 must be open. Exactly those must be open. Some others might be open as well, but we only care about these 3. If the i's warehouse is open, then the j's one must be open as well. Notice that here we are only using the if statement. We are not using the if and only if statement. So essentially what we are saying is, if the i's warehouse is open, so must be the j's warehouse. Okay? But it does not say, so essentially what it means is that if this is 1, this must be 1 as well. But if this is 0, we don't say what should be the value of yj. We are not saying it must be 0. We are saying we don't care. It might be closed, it might be open. We are only saying is one direction implication. If this is true, this must be true as well. We are not saying what should happen if this is false. Okay? And we will see how to formulate this. We can do this. The j's one is open if and only if the i's one is open. So we are really doing both sides. We are saying if the i's one is open, the j's one will be open. If the i's one is closed, the j's one must be closed. So here it's really equivalence that we need to add to our optimization problem. We might say this. The third warehouse can only be open if the first and the second one are open. We can do this, like the third one can be open if and only if first or the second one are open, and so on and so forth. Okay? So essentially we are going to encode logic constraints into our optimization problem. And when dealing with logic, there are some natural rules that, well, you either remember them or you know how to derive them. Okay? So let's do that. If we have a binary variable, say y, and at certain point we want to use the negation of this variable, then we write it as 1 minus y. Does it make sense? Negation. So if y is 0, the negation should be 1, right? And it is. If y is 1, the negation should be 0, and it is. Okay? So the negation we just write as 1 minus the variable, the binary variable. If we have two binary variables, say y1 and y2, and we want to say either this one is true, or this one is true, or both are true. Here, English or means both can be true simultaneously. In Slovak, when we say or, we in fact mean exclusive or, meaning one is true or the other one is true, but not both simultaneously. That's something else. That's the XOR statement. Okay? If we want to say this logic expression is true, that's equivalent to enforcing that y1 plus y2 is larger or equal to 1. Does it make sense? When is this logic expression true? When at least one of these variables is 1, right? And that's exactly here. We require that their sum is larger than 1. Okay? So we can do more. We can do logic multiplication. So y1 and y2, that's equivalent to saying y1 plus y2 is larger than 2. Now, technically speaking, here we could use equality, but it's better to use those inequalities because we only want to keep inequalities in the optimization problem. Okay? Again, does it make sense? When is this logic multiplication true? Only when both of these variables are ones, right? And that's the same kind of combination which satisfies this inequality. If one of those variables is 0, this inequality is not satisfied. So if you want to say, make sure that warehouse number 1 and warehouse number 2 are open, that's the inequality that you would add into your optimization problem. If you want to say, make sure that at least one of them is open, this is the inequality that we add. They are similar, they just differ in the right-hand side, but that right-hand side makes big difference. Okay? We can have implications like y1 implies y2, which is equivalent to y2 larger than or equal to y1. Now, does it make sense? So what we are saying is, if y1 is 0, what should be the value of y2 which satisfies this implication? We don't care. Okay? So the value here can be both 0 as well as 1. However, if y1 is equal to 1, we do require that y2 is equal to 1. Okay? What we can see here is that in both cases we have this relation, right? y2, regardless of what the value is always larger than y1. Okay? So that's why we have this relation. You can always remember that as if you have an implication going to the right-hand side, it's always the right-hand side which is larger than the left-hand side. Okay? And we might have, well, actually, one thing which I don't have there, but which is quite natural. What if we have y2 implies y1, which is nothing else than y1 and this kind of arrow? Okay? These two statements are the same. Using the same logic, it's y1 larger than or equal to y2. Okay? And now finally we have the equivalence between y1 and y2. What equivalence means is that, so if we have the equivalence, then if y1 is 0, y2 must also be 0. If y1 is 1, y2 must also be equal to 1. Okay? So we see that this is nothing else but y1 is equal to y2. By the way, there is even easier way how to remember this. Equivalence is really just implications going in both directions, right? So we have y1 implies y2, and equivalence means that y1 will be implied by y2. We know that this one is y2 equal, larger than or equal to y1, and this one is y1 larger than or equal to y2. What is the consequence of these two inequalities being satisfied simultaneously? Right? That's equality. So we have y1 which is smaller than y2 from the first statement, and it's larger than y2 from the second statement. The only case where this could hold is where they hold this equality. Okay, so that's how this one has originated. Okay, so remember where to find this table. We will use this table as well to derive even more complex expressions. Like here, we are only assuming the logic summation of 2 terms. What if we have logic summation of 3 terms, and so on? We will use these basic rules and combine them together. So let's now move to those practical situations which we might want to model using these kind of techniques, using logic constraints. So at least one of warehouses number 1, 4, and 5 must be open. First, how can we write this in logic terms? We know that we have variables y1, y4, and y5. What do we require about these variables? Remember, this symbol here, it's the logic multiplication, that's AND, and this logic summation, that's OR. So we require ORs here. And we require essentially that this is true, right? Okay. Yeah, that's a good one. Question is, how can we write it as inequalities? Because this we cannot include into our optimization problems. The inequalities we can. So we are now translating the logic statements into corresponding inequalities that we will add as constraints to our optimization problem. So y1, there is a suggestion, plus y4 plus y5, and now what? Like this. Yeah, and that's precisely what it is. Okay. What about this one? That all of them have to be open. So we have y1 and y4 and y5 is true. When is this one true? Which inequality has to be satisfied? Bless you. Is larger than 3. By the way, notice that it's really similar here. This 2 here refers to how many of these variables we have in that statement. Here we have 3 variables, that's why we have 3. In the logic OR, we always have the 1 on the right-hand side regardless of how many variables are there. Okay, perfect. Good. Now we come to the implications. So if the ice warehouse is open, then the JSON must be open as well. So we have an implication of this form. And we already know how to write it. That's just yj is larger than or equal to yi. Such a simple constraint you add, and suddenly you are adding logic into your optimization problem. Okay? If the ice1 is open, then the JSON must be closed. Okay, so here we are going to combine several things. So first, let's write it in mathematical terms. So what we are saying is, if the ice warehouse is open, that should imply that the JSON is closed, right? That's what it says. It only says if. It doesn't say only if and only if. If means to the right. Only if means to the left. If and only if means both. Okay? So how can we now write this as a set of inequalities? Well, that's why we have the first row, which says how to deal with this negation of a variable. How can we equivalently write this? That's 1 minus ij. How do we now write, well, how do we write this as an inequality? Okay, maybe I should have started with that one. Well, first, it's always the right-hand side which is larger than or equal to the left-hand side. Okay, that's what the basic rule says. And now we will rewrite the inequality, well, the negation like this. Okay? And voila, we get this logic into our optimization problem. Okay, one more. If the ice1 is closed, then the JSON must be open, which is really kind of similar. So what do we have there? If the ice1 is closed, then the JSON must be open. Okay. Let's make it something else as on the whiteboard. Say, if the ice1 is closed, then the JSON must be closed. How can we do that? Well, we rewrite this into inequality. So we take the right-hand side, make it larger than or equal to the left-hand side. And step number 2, replace negations by 1 minus the variable. So 1 minus yj larger than 1 minus yi. Okay? So still easy. What about this one? Here we have the equivalence. Okay? And actually what is important here is just to realize that equivalence is really just 2 implications. Okay? So equivalence means that if the left-hand side is true, the right-hand side must be true. And if the left-hand side is false, then the right-hand side must be false as well. And we know how to write this, right? That's just yj is equal to yi. We can also write it as 2 inequalities. That's really the same thing. What about this one? If the jth one is closed, well, the jth one is closed if and only if the ith one is open. So what we really want is the ith one open is equivalent to the jth one's closed. Okay? And we know that equivalence is equality, so it means that yi is equal to 1 minus yj, nothing else. Okay? So that's easy. Okay, and let's finish it up by a couple of more examples of this sort. Okay, actually, no, let's stop here, because here we will start kind of combining, because we have now 3 literals that we need to consider, because we have 3 warehouses that we are considering, okay? So we will cover that on the subsequent lecture. Okay? So thank you very much for your attention, and see you next time.